You know, in chemistry class, we're taught that chemical bonding is pretty black and white. It's either ionic, where an electron gets transferred, or it's covalent, where electrons are shared. But guess what? The reality is so much cooler and, honestly, a bit messier. Today, we're pulling back the curtain on the hidden rules that really govern the huge gray area between these two extremes.
So let me start with a puzzle for you. We've got two compounds here, table salt and aluminum chloride. Both are a metal plus chlorine, so you'd think they'd be pretty similar, right? But they're not even close. Sodium chloride is your classic ionic solid. It won't even think about melting until you hit a scorching 800 degrees Celsius. But aluminum chloride, it basically turns into a gas at just 180 degrees, a temperature you could get in a regular kitchen oven. So what is going on? By the end of this, you're going to know exactly why.
Okay, so here's the secret. Chemical bonding isn't an on-off switch. It's really a spectrum. You've got purely ionic on one end, purely covalent on the other, and, well, most compounds are just living somewhere in the middle. And this all comes down to a really cool phenomenon called polarization, where the positive and negative ions actually start to distort each other, and that leads to some electron sharing.
All right, to really get a grip on this spectrum, we need to talk about two key ideas. First, how good is a positive ion, a cation, at distorting its partner? And second, how easily does the negative ion, the anion, let itself get distorted? It's this fundamental push and pull that is the heart of polarization.
First up, let's talk about polarizing power. This is all about the cation, the positive ion. Think of it like the cation's magnetic personality. Its ability to reach out and pull on that big, fluffy electron cloud of the anion and kind of warp its shape. So a cation with high polarizing power is really good at doing this.
Now, the other side of that coin is polarizability. And this, as you might guess, is a property of the anion. It basically describes how soft or, squishy its electron cloud is. An anion with high polarizability is super easy to distort. Its electrons are just really susceptible to that pull from a nearby cation.
So, what makes a cation a powerful polarizer? Well, it comes down to three things. First, a higher positive charge. Makes sense, right? An aluminum ion with a +3 charge is going to have a way stronger pull than a sodium ion with just a +1 charge. Second, a smaller size. A tiny little lithium ion can get right up close and personal, concentrating its charge way more effectively than a big old potassium ion. And third, a very specific type of electron setup, which is actually super interesting. Let's look at that now. Now, this is where things get really cool, the impact of d electrons. Let's compare a sodium ion and a copper ion. Same charge, pretty similar size. But that copper ion has 10 d electrons. And here's the kicker. D electrons are terrible at shielding the positive charge of the nucleus. They just don't block it very well. This means the effective nuclear charge that the rest of the world feels is stronger for copper, giving it a much higher polarizing power than sodium. Okay, and what about the anion? What makes it more polarizable, more squishy? Two main things. A higher negative charge, which means more electrons creating a bigger, more diffuse cloud that's just easier to push around. And second, a larger size. The electrons in a huge iodide ion are way farther from its nucleus than in a tiny fluoride ion. That makes them less tightly held and way more susceptible to being polarized.
So back in the early 20th century, a chemist named Casimir Fajan put all of these pieces together into a really simple but powerful set of guidelines. And today, we know them as Fajan's rules. They are key to predicting just how much covalent character you'll find in what looks like an ionic bond.
And here's the most important point, the whole shebang right here. When you have a powerful polarizing cation meet a squishy, susceptible anion, things get interesting. The cation distorts the anion's electron cloud so much that the electrons aren't just transferred anymore, they actually start being shared, and the result is a bond that acts a whole lot more like a covalent bond. This changes everything about the compound's properties, like its melting point.
And here they are, the rules in a nutshell. If you want to find significant covalent character, this is what you look for. A small cation with a high positive charge, a large anion with a high negative charge, and ideally a cation with that pseudo-noble gas configuration full of those poorly shielding d electrons. Seriously, write this down. Screenshot it. This is a huge exam tip.
This table is a great way to see it all side by side. Just look at the pattern. Everything that packs that positive charge in tight, like a small cation or a high charge, drags the bond over towards the covalent end of the spectrum. On the other hand, big, spread-out ions with low charges, they just don't have the polarizing muscle, and the result is a much more purely ionic bond. All right, Enough theory, let's put these rules into action and solve some real chemical mysteries, starting with that very first one I showed you.
Remember this crazy chart? Sodium chloride way up at 800 degrees. Magnesium chloride, okay, a bit lower, at 712. And then aluminum chloride just plummets off a cliff, turning to a gas at 180. The trend is just, wow, it's undeniable. And here is the answer. It's Fajan's rules in action. As we go from sodium to magnesium to aluminum, the charge on that cation jumps from +1 to +2 to +3. This massively increases its polarizing power. The bond in aluminum chloride has so much covalent character that it doesn't even form a strong ionic lattice anymore. Instead, it forms these little discrete molecules, which take way less energy to pull apart. And that's why it has that incredibly low sublimation point. Mystery solved. Here's another perfect example. Lead can form two different chlorides. In lead-2 chloride, the Pb2+ ion is less polarizing, the compound is a solid, melts at a respectable 501 degrees, but in lead-4 chloride, that highly polarizing Pb4+ ion, man, it creates a bond that is way more covalent. The result? It's a liquid at room temperature that freezes at -15°C. What a difference a charge makes. You know what else Fajan's rules explain? Some really weird solubility patterns. You expect ionic salts to dissolve in polar stuff like water, right? Not in organic solvents like ethanol. But lithium chloride is the rebel. It breaks this rule. And why? Because that lithium ion is teeny tiny, giving it a high polarizing power for its charge. This gives lithium chloride just enough covalent character to feel comfortable dissolving in less polar organic solvents, something other alkali chlorides just won't do.
The rules also line up perfectly with trends in thermal stability. To decompose a carbonate, you've got to break that carbonate ion apart. Well, the tiny beryllium ion, Be2+, is so polarizing that it aggressively distorts the carbonate's electron cloud, making the whole thing really unstable. It just falls apart at a measly 100 degrees Celsius. But as you go down the group, the cations get bigger, they get a little lazier, less polarizing, so you need to crank up the heat way, way higher to get them to decompose.
Okay. Let's wrap this all up and build your personal toolkit for predicting covalent character. This is everything you need to know to absolutely ace any exam question on this topic. So next time you're looking at a compound, just run it through this simple 3-step check. Step 1, analyze the cation. Is it small, highly charged? Does it have d electrons? Step 2, analyze the anion. Is it large, highly charged? If you're nodding your head yes, then you go to step 3 and conclude high polarization is happening here and this compound is going to have significant covalent character. It's that easy. So please, let's get rid of this old, oversimplified idea that metal plus nonmetal always equals ionic. It's just not true. The reality, the more accurate and powerful view, is that bonding is a spectrum. And Fajan's rules are the tool that lets you predict exactly where on that spectrum a compound is going to fall.
And I'll leave you with one final challenge to chew on. Silver can form both silver chloride and silver iodide. Now, the cation, the silver ion, is the same in both compounds. So using what you've just learned from Fajan's rules, which one of these would you expect to have more covalent character and why? Think about the anion.
Thanks for watching.